In the previous lectures, we showed how the slope deflection method can be used to analyze continuous beams. In this lecture, we're going to examine the use of the method for analyzing frame structures. Consider a two-story frame structure fixed at the base. The frame has 6 joints. So there are 6 joint rotations. 2 of these rotations are known. Theta A and theta B are 0 since the frame is fixed at A and B. However, joint rotation at C, D, E, and F are unknown. Also, we consider moment reaction at A and B as unknown. Let's refer to them as MA and MB. Further, under the applied loads, the frame is going to deform like this. Let's refer to the lateral displacement at the top of the first story as delta 1, and we use delta 2 for the horizontal displacement at the top of the second story relative to the first story. These displacements are also unknown. Therefore, we have a total of 8 unknowns. There are 4 unknown slopes, 2 unknown displacements, and 2 unknown moment reactions. We need 8 equations for determining these unknowns. 6 of these equations come from the moment equilibrium condition for the joints. They are the remaining 2 equations come from a rigid body equilibrium condition applied to 2 distinct parts of the frame. More specifically, one of the equations is obtained by cutting the frame at the first level like this, and summing the forces in the x direction like this. The other equation comes from cutting the frame at the second level like this. Then, summing the forces in the x direction gives Since we can express these shear forces in terms of member and moments, all 8 equations can be written in terms of the unknown slopes and deflections. We can then solve the equilibrium equations simultaneously for the unknowns. Once the slopes and deflections are determined, we can calculate the member and moment and shear forces and determine support reactions. Let's go through an example to see this process in action. Here is our 2-story frame. For the sake of simplicity, we assume a constant EI for the entire structure. Since the frame has a side sway, the slope deflection equations for the vertical frame members embody the non-zero deflection term. So for member AC, we have for BD, we get for CE, we can write and for DF, we have the deflection term, however, is 0 in the slope deflection equations associated with the horizontal members. So for CD, we can write and for EF, we get Here are our 6 joint equilibrium equations in the expanded form. We can use the slope deflection equations to expand the equilibrium equations to rewrite them in terms of the unknown slopes and deflections. As for the remaining two equations, let's replace each shear force with its corresponding member end moments. But how? How do we express shear in terms of moments? For a typical vertical frame member, we can draw its free body diagram like this. Taking the sum of the moments about point J, we get, or, then VAC becomes, VBD is, VCE can be written as, and here is VDF. So the last two equilibrium equations can be written this way. Solving all 8 equilibrium equations simultaneously, we get when we substitute these slopes and deflections in the slope-deflection equations, we get the following values for member end moments. Now we can calculate member end shear forces like this. Now we transfer member end shear forces to the joints and apply the equilibrium conditions to each joint until support reactions are determined. But since moment equilibrium has already been maintained, at this point we only need to consider force equilibrium at each joint. Let's start by transferring member end shear forces to the joints. Here is the transfer for member EF. For member CE, for DF, for CD, for AC, and for BD. Now we enforce the equilibrium conditions. For joint E, we get for joint F, we have now we transfer the axial force in member CE applied to joint E to joint C. Then we balance the forces at joint C. Transferring the axial force in member DF applied to joint F to joint D, and balance the forces at joint D. Now let's transfer the axial force in member AC applied to joint C to joint A, and do the same for member BD. Finally, apply the equilibrium conditions to joint A to determine the support reactions at A. Do the same at B in order to determine the reaction forces at B. We've already determined moment reactions at A and B. Here are the remaining support reactions. Now it's your turn.